As promised, here are the stoichiometry problems that we did during class. I said I would work through them for everyone so that we get an idea what we need to do for the stoichiometry test. So I'll try to get all of this done in one video, although I can't guarantee that I'll have enough space to get every one of these problems on to one video. So for this one, we have the Haber process, which, as I said, is one of the most important reactions in all of the history of the world, where we can take nitrogen, which is available in the atmosphere but not available to plants. We will use hydrogen from water, which can be easily extracted from water, and we can make ammonia. This is the building block for fertilizers. This is how we can sustain the population we have on this planet. We need chemical fertilizers in order to make that happen. Now the question is, how many moles of ammonia are produced when 5.0 moles of hydrogen reacts with an excess of nitrogen? So in this case, hydrogen is going to run out. We have more nitrogen than we need. Only the hydrogen is going to run out. So what I do, I write down what I am familiar with. Now, for stoichiometry, we have a balanced equation. We go units to moles. Now in this particular case, we're lucky because the units are moles already, so we don't actually have to do a mole conversion. So I have 5.0 moles of hydrogen. Then after that we find the mole ratio, which is 1 to 3 to 2. Now I can actually make this conversion in one of two ways. I have 5 moles of H2. I could make this a cross multiplication. I don't know how many moles of ammonia. So X moles of ammonia. Now I apologize, I'm writing this kind of on the side because that's the way I'm seated. But that would equal my mole ratio here, which is 3 moles of H2 in general to 2 moles of NH3. Now the cross multiplication, I end up getting 3x equals 5 times 2, which is 10. Divide both sides by 3, and I get 10 divided by 3, 3.3 repeating moles of ammonia. We have to keep track. We have to make sure we know what we're talking about, right? Solve for X moles of ammonia, X moles of ammonia. Now, there is another way of doing this in addition. I could just take my 5 moles of hydrogen and then I multiply that by my actual mole ratio. Again, I want to keep track of what goes where. So I have 2 moles of ammonia, because that's what I want to keep, over what I want to cancel out. 3 moles of hydrogen. Where did I get that? I got that from my mole ratio in my balanced equation. As I said, I agreed on your test to give you the balanced equation, so you don't have to worry about balancing. What I really want you to focus on are the steps of stoichiometry. So I get 5 times 2, which is 10. Moles of hydrogen cancel out. I get 10 thirds moles of ammonia, which is equal to 3.3 repeating moles of ammonia. Now in stoichiometry, you always have to focus. What do I have? What do I need? The question here is asking how many moles of ammonia are produced. Well, that's all I needed to do. Of course, you cannot forget your mole conversions. So we have 22.4 liters of gas at STP is 1 mole. We have our gram molar mass, 1 mole. And I have my 6.02 times 10 to the 23rd. I say particles, it really means atoms or molecules over 1 mole. So if I needed to change this in any way, I could take this. Ammonia is a gas, so I could take 3.3 repeating, multiply it by 22.4. My moles would cancel out. I get how many liters of gas I have. I could multiply it by the gram molar mass, which is 17. I get how many grams of this I have. I could also do 6.02 times 10 to the 23rd. Find out how many molecules of ammonia I have. These three conversions are all you need to know. Of course, you have to do them the opposite way too, which we'll do it a little bit later. Second problem, I think I have to make sure I'm bound. Yeah, I have to slide this up a bit. I don't have Khan Academy money, so I have to be very old-fashioned, but calculate the number of moles present in 9.5 grams of CO2. So, first thing I do, 9.50 grams of CO2. Saying find the number of moles. So, it's the inverse of what I've done before. I have 1 mole over the gram molar mass of carbon dioxide. That's 12. 2 oxygens is 32. 12 plus 32 is 44 grams. Which means, how many moles? 9.50 divided by 44 equals 2. So my grams cancel out. I end up getting 0. Now this is 3 significant digits. This is really 2 significant digits. But I'll give myself 216 moles of CO2. Make sure you write the units. That way I check. I need moles of carbon dioxide. I need moles of carbon dioxide. So we're good. Next one, yttrium, metal, tarnishes slowly in air and burns readily to form yttrium-3 oxide. Find the number of moles of yttrium oxide produced. Again, we've got to be able to say what this means. So I have yttrium. That is on the periodic table. I have oxygen. That occurs as a diatomic element always. It always occurs as a molecule. This produces yttrium-3 oxide. Now I can do it my easy way. Oxygen is always a -2. Since this is yttrium-3, it's a +3. How do I get this to balance? I make this a 3. I make this a 2. Remember, the 3 refers to the charge on the atom. It does not refer to the number of atoms. So yttrium-3 oxide is that. In order to make this work, I would need 2 yttrium-3 oxides, which means the reason why I need 2 is because I have 3 here. They always come in pairs. So now I have 3 oxygens, that's 6 oxygens, 3 oxygen molecules, that's 6 oxygen atoms, 6 oxygen atoms, and I have 4 yttrium atoms in order to balance this equation. So yttrium metal tarnishes slowly in air and burns readily to form yttrium-3 oxide. Find the moles of yttrium-3 oxide produced from 3.33 moles of yttrium. Okay, so my balanced equation is this balanced equation. From there, I have what I write down what I know. 3.33 moles of yttrium. Now, what's the question asking? How many moles of yttrium-3 oxide are produced? We assume there's an excess of oxygen, which means we have more oxygen than we need. What we're going to run out of is the yttrium. So I need to find yttrium-3 oxide. Well, I have yttrium-3 oxide. I'm not going to do the cross multiplication because this way is just as effective and it saves me a little bit of space. So I want 2 moles of yttrium-3 oxide. It's here, 2 moles, because that's my mole ratio in my chemical reaction. And then 4 moles of yttrium. So it's 3.33 times 2, which is 6.66, divided by 4, means that my moles of yttrium cancel out. All I'm left with is moles of yttrium, and I get 1.665 moles of yttrium-3 oxide. Is that what it's asking for? Find the moles of yttrium-3 oxide produced from 3.3 moles of yttrium. I got it there. Now, just to be clear, that has 3 significant digits. This bottom one should also have 3 significant digits, so we'll call this 1.67 moles of yttrium oxide. That would be the best answer for that particular problem. And I hope that everything fits, yes. Okay. Next, turning the page. I have to align these, which means I have to stand up. Copper reacts with silver nitrate to produce silver and copper 2 nitrate. This is a nice, good single replacement reaction. I take copper, I drop it in silver nitrate. Ag has a +1, nitrate has a -1, and the formula unit is balanced. This will yield silver. Now, copper 2 nitrate, which means copper has a +2 charge, which means I need 2 nitrates with a -1 charge to balance it. There we go. Now, if I can right away see that I have 2 nitrates here, which means I need 2 nitrates here, which means I'm going to need 2 silvers. Now I have 1 copper, 2 silvers, 2 silvers, 2 nitrates, 2 nitrates. I'm completely balanced. Now it says 40.7 grams of silver is produced. Calculate the number of moles of each reactant. So, I have my balanced equation. I have something that I can use to get more information. 40.6 grams of silver. Now, what do I do with those units? I have to turn them into moles. First step is balanced equation. Second step is units to moles. I need to find my gram molar mass for silver, which I can see right here is 107.87. One mole, because I want to cancel out 107.87. We'll call that 0.9 grams. That's the gram molar mass for silver. My grams cancel out. I get 40.7 divided by 107.9, which equals 0.377 moles, because that's the only unit I have left, of silver. Now, silver is a product. However, the mole ratio will help me find out how many moles of each reactant I had. So, I start with 0.377 moles of silver. First reactant I want to look at is copper. So I want to have my copper on the top. Now notice, 1 mole of copper is going to give me 2 moles of silver. That's why that mole ratio is important. So now I do 0.377 times 1 divided by 2. My moles of silver cancel out. I'm left with copper. Divided by 2 equals 0. So we'll call this 0.189 moles of copper. That is what is left here. And then I also have to find out my other reactant, which is silver nitrate. 0.377 moles of silver. I'm still using that because that is what I have in my reaction. Now, what's my mole ratio? What do I want to cancel out? I want to keep silver nitrate on top, and I have 2 moles of silver. Where did I get those? I got those straight from my balanced reaction. So 0.377 times 2 divided by 2, it is still 0.377 moles of silver. This cancels, silver nitrate. It says, calculate the number of moles of each reactant. My reactants are copper and silver nitrate. I have my moles of copper, I have my moles of silver nitrate. That tells me that I did everything that I needed to do. The next one is not a balanced reaction. I think I have to focus a little bit better. Okay. So under the right conditions, ammonia can be converted into nitric oxide. To zoom out a little bit more. Under the right conditions, ammonia can be converted to nitric oxide. That would be this right here. Or nitrogen monoxide. How many molecules of oxygen are required to react with 6 grams of ammonia? Now, at first, looking at this, I might realize right away this is not balanced. So the question is, how do I balance this particular reaction? I have 2 oxygens, 1 nitrogen, but I have 2 hydrogens, 3 hydrogens. Now, the first step I might do is do a 2 here. That would be a 3 here. Why? Because I have 6. If I double this, I have 6 hydrogens. I have 6 hydrogens. Now my hydrogens are balanced. However, I have 2 nitrogen monoxides. I have 2 nitrogens. I have 2 oxygens, 3 oxygens. That's 5 oxygens. Very hard to get 5 oxygens with an O2. So the only way I can do this is by going, we'll say 5 halves of O2. Now these are not whole numbers. What am I going to do eventually? I'm going to double this, double this, double this, and double that. So I end up, my balanced reaction is 4 ammonia plus 5 oxygen plus, yields 4 nitrogen monoxide plus 6 water. That is my balanced reaction. Now, how many molecules of oxygen are required to react with 6 grams of ammonia? I write down what I know. 6.00 grams of ammonia. I have my balanced equation. That's step 1. Step 2 is units to moles. This one I do have to change to moles because that is a gram value. So 1 mole over 17 grams. Where did that 17 come from? The molar mass for nitrogen is 14. Molar mass for hydrogen is 3. Molar mass for hydrogen is 1, but I have 3 atoms. 14 plus 3 is 17. So now, how many moles of ammonia do I have? My grams cancel out. 6.00 divided by 17 equals 0.35294118. I'm going to call that 353 moles of ammonia. Now, with that, it says now, how many molecules of oxygen? So I want to take this and use this with my mole ratio to find out how much oxygen I need to react. So 0.353 moles of ammonia. This ratio is based on moles, so I want to keep it in moles with my mole ratio. I want to cancel out my moles of ammonia. I want to keep my moles of oxygen. Moles of ammonia now cancel out. I have 0.353 times 5 divided by 4 is 0.441 moles of oxygen, because that's the only thing I have left after my other units canceled out. But what the question is asking is how many molecules of oxygen. So you remember we have a couple of different conversions. One of them is number of particles, in this case molecules. So 0.441 moles of O2 The magic number for converting to number of particles is 6.02 times 10 to the 23rd particles, in this case molecules, over 1 mole. The question is asking how many molecules of oxygen. So I do 0.441. Let me just double check my numbers up top because I got something weird. 0.353 times 5 equals, divided by 4 equals, okay, times 6.02 is 265.656. So I'll round that up to 2.656, except I can't leave it like that because I have this 10 to the 23rd that I need to keep. And I'll see if all of that fit. Barely fit. 2.66 times 10 to the 23rd molecules of O2 is my answer. Again, we know these mole conversions. We can't forget these mole conversions. All right, turning the page. Let me line this up as it needs to be lined up. Okay, use the reaction below for the combustion of methanol. Any type of stoichiometry problem is possible. Now that, don't worry about that. That is just something CK12 wanted to put out there. This is my balanced reaction. Now someone might say, I don't know what methanol is. Well, hopefully you know that is water, that is carbon dioxide, that is oxygen. By process of elimination, that is methanol. Methanol we've talked about before. It's methane, except instead of one of those hydrogens, we now have an OH. It has hydrogen bonding. It burns without a visible flame. Scary stuff. But anyway, what mass of methanol, that's what I want to find, is combusted in a reaction that produces 112 liters of CO2. So what do I know? I know I have 112 liters of carbon dioxide. I have a balanced equation already. That's always step one. Step two is to figure out how many moles, units to moles. This is liters. So again, we have to make sure we're doing the right conversion. 1 mole over 22.4 liters at STP. Every gas, and carbon dioxide is a gas, occupies 22.4 liters at STP. So here we go, 112. My liters cancel out. I'm left with moles. 112 divided by 22.4 is 5. 5 moles of CO2. So I did my balanced equation, units to moles. Now what are we looking at? We're looking at carbon dioxide and we're looking at methane. This works forwards, this works backwards. If I have 2 moles of methanol, I'm going to make 2 moles of carbon dioxide. You can do the reverse process. It takes some energy, but I can take carbon dioxide, combine it with water, and make methanol. If I have 2 moles of carbon dioxide, I'm going to make 2 moles of methanol. So, in this case, I have 5 moles of carbon dioxide. I'm going to feed this through my mole ratio to find moles of methanol. So, 2 moles of methanol over 2 moles of carbon dioxide. I set this up so that my moles of carbon dioxide cancel out. I get 5 times 2 divided by 2, which is 5 moles of methanol. I have to slide this up a little bit because that is not what the final answer is. We're pretty close though. I have 5 moles. What did I do? Balanced equation, units to moles. I found my mole ratio. I multiplied to cancel out carbon dioxide to keep methane. If I set up a cross multiplication, it'd be the same exact thing, but this is a little bit faster in my opinion. Now, I did my cross multiplication or my canceling out. Now I have my moles of what I'm interested in, methanol, and I need to go to grams. So I'm going to put moles on the bottom so that it cancels out. The gram molar mass here, we have 12. Hydrogen is 1. We have 3 of them. We actually have 4 of them. So 12 plus 4 is 16. 16 plus 16, because oxygen is 16, is 32. 32 grams over 1 mole. So 5 times 32 will give me the grams of methanol. 5 times 32 equals 160. So keep track of what you're doing. 160 grams of methanol is required to produce 112 liters of carbon dioxide. This is a pretty nice stoichiometry problem. That is something that you will see, something very much like that on a test. Now, this one is definitely one where I would give you the compounds. Now, use the reaction below for the decomposition of sodium azide. You might say, what is sodium azide? Well, in this particular case, this is sodium metal, Na by itself. This is nitrogen gas, N2 by itself. This has got to be sodium azide. Azide is a weird sort of a polyatomic anion. It has a -1 charge. It's made of 3 nitrogen atoms put together. Now this is how this equation is balanced. 2 sodium azides, 2 sodiums, 3 nitrogens. Again, it gets a little complicated because nitrogen is N2 in its natural form. What volume of nitrogen? This is the reaction that happens inside of airbags. You want to be very careful about how much sodium azide you put into an airbag. If you put too little, you're going to smash your face into the steering wheel. If you put too much, you're going to end up popping the bag or knocking yourself out because of all the gas that whacks you in the face. Either way, it has to be very carefully balanced. So if I put 130 grams of sodium azide, how many liters of of nitrogen gas at STP would I produce? So I write down what I know. 130.0 grams of sodium azide. First thing I'm going to do is get my balanced equation. I have that. What's the next thing? Units to moles. Always units to moles. So 1 mole over sodium azide. Sodium is 23 and nitrogen is 14 times 3 would be 42 plus 23 is 65 grams of sodium azide. If I really want to, you can never write too much because that way you're absolutely sure what you're doing here. So 130 divided by 65 is going to give me 2. These units cancel out. I'm left in moles. 2 moles of sodium azide. That was my next step, right? I have my balanced equation, then units to moles. Then from there I use my mole ratio. I'm interested in nitrogen. So I'm going to have 2 moles of sodium azide. And then I'm going to feed that through my mole ratio. What am I interested in? I'm interested in 3 moles of nitrogen over 2 moles of sodium azide. That way the moles of sodium azide cancel out. And I get 2 times 3, which is 6, divided by 2, which is 3. I mean, I can see that. 6 times 2 is 3. I'm sorry, 2 times 6 is 6. 2 times 3 is 6. And then divided by 2 is 3. And what am I left with? Nitrogen. So that is 3 moles of nitrogen. But that is not what the question is asking at the end. I just need to see if I need to move this up a little bit. It's asking for the volume of nitrogen at STP. Well, I have 3.00 moles of nitrogen. I multiply that by 22.4 liters. I hope we know nitrogen is a gas. It's all around us. 79% of our atmosphere is nitrogen. So 3 moles of nitrogen. This way, 1 mole occupies 22.4 liters. My moles cancel out. I end up with 3 times 22.4, which is, I believe, 67... times 3 is 67.2. That's what I thought. Okay. 67.2 liters of, in this case, nitrogen. Make sure you write down your units because it's asking for volume. We measure volume with liters. If it's asking for mass, you want to have grams. If it's asking for particles, you want to say if it's atoms or molecules. You've got to keep track of your mole conversions. Okay. We have one more side of this sheet, 2 more problems to get through, and again, these are very much like you will see on a test. Now again, I'm not Khan Academy, so I'll do all this by hand, but here we go. Ammonia and copper oxide, which actually should be copper 2 oxide, react to form copper, water, and nitrogen as shown in the following reaction. If a sample of 51.0 grams of ammonia was reacted with excess copper oxide, how many moles of nitrogen would be produced? So the copper oxide, even though it's named wrong, we have more than we need of that. 51 grams of ammonia is what we need to focus on. 51.0 grams of ammonia. I have my balanced equation. Next step is units to moles. So, 1 mole, units to moles. I want to cancel out my grams. Over 17 grams. 51 divided by 17, I believe is 3. 3 moles. Okay. Now, that's how much ammonia goes in. Once this ammonia is used up, the reaction stops. It's asking how many moles of nitrogen. It's not asking for grams, it's not asking for liters, it's only asking for moles. But I start with 3 moles of ammonia, and from there, I'm worried about nitrogen. So it's 1 mole of nitrogen over 2 moles of ammonia, which I get from my balanced equation. The moles of ammonia cancel out. 3 times 1 is 3, divided by 2, 1.5 moles of nitrogen. In this case, it says how many moles of nitrogen will be produced. I have moles of nitrogen. I'm done. Now, if I wanted to take that and convert it, I still shouldn't forget my conversions. I would not be this kind to just have you tell me moles on a test. So if I wanted to convert that to grams, N2, 2 nitrogens, each nitrogen is 14, 2 nitrogens, 28 grams over 1 mole. So my moles cancel out. That would give me the gram value. In this particular case, 1.5 times 28 is 42 grams. I might ask you for how many grams of nitrogen. I might ask you for how many molecules of nitrogen. 1.5 moles of nitrogen times 6.02 times 10 to the 23rd molecules over 1 mole. My moles cancel out again. And I end up with 1.5 times 6.02, whoops, 1.5 times 6.02, 9.03 times 10 to the 23rd molecules. See if all of that fit. Didn't quite fit. 9.03 times 10 to the 23rd molecules. Or I could ask you for liters of gas because nitrogen is a gas. So 1.5 moles of nitrogen times 22.4 liters over 1 mole. My moles cancel out again. 1.5 times 22.4 equals 33.6 liters of nitrogen gas. Okay, last one, then we're done. I said this is a limiting reactant problem. All it's asking is, which is the limiting reactant? We'll do a couple more problems like this, but you will definitely see something like this on a test. I just have to make sure I line everything up. So, I have my balanced equation. 2 aluminums, 2 aluminums. 3 oxygens, 3 oxygens. 2 irons, 2 irons. I'm good. There are 10 grams of aluminum and 20 grams of iron 3 oxide reacting. Remember, iron 3, the charge is plus 3. I have 2 plus 3s, it's balanced by 3 minus 2s. So this is iron 3 oxide. There are 10 grams of aluminum and 20 grams of iron 3 oxide reacting. Which is the limiting reactant? I will add, this is the thermite reaction. Very exothermic. Lots of energy gets produced. So I have 10.0 grams of aluminum. I have 20.0 grams of iron 3 oxide. First thing, I have my balanced equation. Second thing, units to moles. Aluminum is, its gram molar mass is 27. I could find that on the periodic table. 10 divided by 27 means I have 0.370 moles of aluminum. Iron 3 oxide is a little bit harder. Iron is 55.8. I have 2 of them. So 2 times 55.8 is 111.6. I'm adding that to 3 times 16, which is 48. And that ends up giving me 159.6 is the gram molar mass for iron 3 oxide. 1 mole over 159.6 grams. My grams cancel out. 20 divided by 159.6 is 0.125 moles of iron 3 oxide. Now, thinking about this, for every, if I can see my equation at the top, for every 2 moles of aluminum, I need 1 mole of iron 3 oxide. So basically I need double or half. I need double the amount of iron 3 oxide in aluminum. So if I take this number, multiply it by 2, I get 0.250 moles of aluminum. What that tells me is if all of my iron 3 oxide reacts, how much aluminum will I need? I'd need double the amount of aluminum. So that'd be 0.250 moles of aluminum. Do I have that? Absolutely I have that. Now if I needed to do all of my aluminum reacting, I would need 1/2 the amount of iron 3 oxide. In that case, it would be 0.370 divided by 2, which is 0.185. So for all of my aluminum to react, I would need 0.185 moles of iron 3 oxide, except I don't have that much. So once this amount runs out, I'm done. That's the limiting reactant. That's why, for this particular case, iron 3 oxide would be the limiting reactant. How much aluminum would be used up in this case? 0.250 moles of aluminum would be used. How much would be left over? It would be 0.370 minus 0.250, so 0.120 moles of aluminum would be excess, left over. Once this gets used up, the reaction stops. This reaction is going to use up that much aluminum. You're going to have that much aluminum left over. So if there were a question like how much aluminum is left over at the end of this reaction, then I would know that it's 0.120 moles of aluminum because that's my excess, right? I had this much aluminum. I only needed this much. Whatever is above this amount is left over. And then I would do 27 grams because that's the gram molar mass of aluminum. 1 mole. My moles cancel out. And I end up getting 0.120 times 27. I would have 3.24 grams of aluminum left over that is not participating in this reaction. So there is the entire worksheet. Took us about 41 minutes to get through. I hope that this is helpful. See you soon.